Skew Symmetric Matrices. Hello everyone. To begin today's lesson, let's first look back at what we covered in our previous section, where we discussed symmetric matrices. As you recall, the defining characteristic of a symmetric matrix is that it remains completely unchanged after transposition, meaning that if you swap its rows with its columns, the matrix stays exactly the same. Now, we are going to explore a closely related but distinct concept, the skew symmetric matrix. While it is similar to the symmetric matrix we just studied, it behaves differently when transposed, and we will examine exactly what that means and how to identify these matrices in the upcoming slides. Definition of skew symmetric matrix. Now that we have reviewed symmetric matrices, let us move on to the definition of a skew symmetric matrix. First, it is important to note that we are dealing with a square matrix, which we will call matrix A. A square matrix is said to be a skew symmetric matrix if the transpose of the matrix is equal to the negative of the original matrix. To express this mathematically, matrix A is skew symmetric if a transpose equals negative A. If we look at this in terms of the individual elements within the matrix, for all possible values of the row index I and the column index j, the element at row j and column I is equal to the negative of the element at row I and column j. To put this in simpler terms, if you swap the row index with the column index, the numerical value of the element remains the same, but its sign changes. This means a positive value becomes negative and a negative value becomes positive. As we will see in the next slide, this specific relationship between elements leads to a very important rule regarding the diagonal of the matrix. The property of diagonal elements. Now that we have established the definition of a skew symmetric matrix, let us look at a critical characteristic that you must always remember. All diagonal elements of a skew symmetric matrix must be zero. You might wonder why this is the case, so let us walk through the logical derivation together. First, let us refer back to the definition we just discussed. We know that for a skew symmetric matrix, the element in the jth row and ith column is equal to the negative of the element in the ith row and jth column. Now, let us consider the diagonal elements. For these specific elements, the row index is equal to the column index, meaning I equals j. If we substitute this into our definition, we find that the element a sub I must be equal to negative a sub I. To solve for this value, we can move negative a sub I to the left side of the equation. This gives us a sub I plus a sub I equals 0. Simplifying this expression, we get 2 times a sub I equals 0. Finally, if we divide both sides by 2, we arrive at the result that a sub I equals 0. In conclusion, this proves that every single element on the main diagonal must be 0 for a matrix to be classified as skew symmetric. Keep this rule in mind, as it is the quickest way to identify or verify a skew symmetric matrix, which we will see in the illustrative example in the next slide. Illustrative example. Our objective here is to verify whether a given matrix is skew symmetric. Let us examine matrix A. This is a 3x3 square matrix. Looking at the elements, the first row consists of 0, 2, and negative 5. The second row contains negative 2, 0, and 4, and the third row contains 5, negative 4, and 0. Before we even begin the calculations, notice that the main diagonal elements are all 0, which aligns with the property we discussed in the previous slide. To formally verify if this is a skew symmetric matrix, we will follow a 3-step process. Step 1 is to find the transpose of matrix A, which we refer to as a prime. To find the transpose, we simply convert the rows of the original matrix into columns. For instance, the first row, 0, 2, and negative 5 becomes the prime column. After performing this for all rows, we get a new matrix where the first row is 0, negative 2, and 5. The second row is 2, 0, and negative 4, and the third row is negative 5, 4, and 0. Step 2 is to find the negative of the original matrix, denoted as negative A. To do this, we multiply every individual element of matrix A by -1, which essentially means we reverse the sign of every non-zero element. 0 remains 0, 2 becomes -2, and -5 becomes +5. Following this process for the entire matrix, we obtain a result where the first row is 0, -2, and 5. The second row is 2, 0, and -4, and the third row is -5, 4, and 0. Finally, in step 3, we compare the results of the first two steps. By observing the two resulting matrices, we can see that a prime is exactly equal to -A because the transpose of the matrix is equal to its negative. We have satisfied the mathematical definition of a skew-symmetric matrix. Therefore, we can conclude that matrix A is indeed a skew-symmetric matrix. Now that we have established the theoretical definition and the critical rule regarding diagonal elements, let us apply these concepts to a practical example to see how they work in tandem. Keep this process in mind, as we will soon look at a real-world analogy to understand why this mathematical property is useful, and we will also discuss some common pitfalls to avoid during these calculations. Real-world analogy. Now that we have verified a numerical example, let us move to a real-world analogy to help you visualize why these matrices behave the way they do. Think of skew symmetry as a net-zero exchange system. To understand this, imagine a table that tracks the flow of resources between 3 different cities. For instance, if City A gives 2 units of a resource to City B, then from the perspective of City B, it is receiving those 2 units from City A. In a mathematical model, we would represent the flow from City A to City B as +2. Consequently, the reverse flow, from City B back to City A, must be represented as -2. This is exactly what we saw in our previous slides where the element at row I, column J, is the negative of the element at row J, column I. Furthermore, it is logically impossible for a city to exchange resources with itself. Therefore, the flow from City A to City A must be 0. This perfectly explains the critical characteristic we derived earlier, that all diagonal elements of a skew-symmetric matrix must be 0. As you can see, this system mirrors the properties of a skew-symmetric matrix perfectly. Now, keeping these rules in mind, let us look at the next slide to discuss some common mistakes you should avoid during your exams. Common mistakes to avoid. Now that we have walked through the definition, the mathematical derivation, and a practical example, let's discuss some common pitfalls. It is important to be aware of these frequent errors to ensure your calculations are accurate. First, let's address the issue of ignoring the diagonal. As we proved in our earlier discussion on the properties of diagonal elements, every element on the main diagonal must be 0. A common mistake students make is forgetting to verify this first. Please remember, if any single element on the main diagonal is non-zero, the matrix cannot be skew-symmetric, no matter what the other elements are. Next, be very careful to avoid sign errors during transposition. I often see students changing the signs of the elements while they are swapping the rows and columns. It is crucial to remember that the process of transposing a matrix only involves moving the positions of the elements. The actual change in sign only occurs during the second step, when you are calculating the negative of the matrix, known as -A. Finally, do not confuse symmetric matrices with skew-symmetric matrices. To keep them distinct, remember that for a symmetric matrix, the transpose of A is equal to A, which acts like a perfect mirror image. In contrast, for a skew-symmetric matrix, the transpose of A is equal to -A, which we can describe as a negative mirror image. Keep these points in mind as we move toward our final summary of the key takeaways. Key takeaways. First, let's revisit the primary condition. A square matrix A is considered skew-symmetric if the transpose of A is equal to -A. This is the fundamental definition we used in our illustrative example to verify the matrix. Secondly, if we look at the individual elements, the relation is that the element in the ith row and jth column is equal to the negative of the element in the jth row and ith column. Essentially, swapping the indices flips the sign of the value. Third, remember the critical diagonal rule we derived earlier. All main diagonal elements, represented as a sub-II, must always be 0. As we saw in our logical derivation, this is a non-negotiable characteristic of any skew-symmetric matrix. Finally, a very important requirement to keep in mind is that only square matrices, those with an equal number of rows and columns, can be classified as either symmetric or skew-symmetric. To wrap up our lesson on this topic, let's go through the key takeaways to ensure you have a solid grasp of the concept before we move forward. If you keep these 4 points in mind, you will be able to identify and verify these matrices accurately in your exercises.